Hello students, this is Rudradeep sir, and today I am going to give you a lesson on the chapter surface chemistry, which is there in your syllabus. Okay, just look at the board. Okay, surface chemistry. This is a total theoretical chapter. Okay, it practical application is there, but practically from this chapter is there in our syllabus. Okay, so here today we are going to discuss on a particular topic which is known as adsorption. What is it? Adsorption. Adsorption. This must be a new term for you, but I am telling you, adsorption is nothing new. It is a very much old concept. So don't just get confused, and let me explain to you what is it. You must have heard this word absorption, right? So what is the difference between this absorption and adsorption? Absorption, you know, everyone knows, I think, what is absorption. What is adsorption? Is a special kind of absorption. Adsorption is a special kind of absorption. Absorption is a bulk phenomena and adsorption is a surface phenomena. Let me explain it to you very easily. Suppose there is a substance which has a tendency to absorb. If it absorbs the adsorbate from each and every part of its body, then the phenomena will be called as absorption. If same type of substance is taken and only surface molecules are the one which are absorbing the adsorbate, then the phenomena will be known as adsorption. Okay, if only surface molecule absorbs, then it will be called as adsorption. If whole body absorbs, then it will be called as absorption. Here is the difference, nothing else. So let us continue what is adsorption. We shall continue with adsorption. So what will be the definition of adsorption then? What will be the definition? Actually, the definition of adsorption is accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed as adsorption. Understood? Accumulation of the adsorbate or molecular species at the surface rather than in the bulk of a solid or liquid is termed as adsorption. From this definition we can get that adsorption is a surface phenomena where some molecular species are involved to the surface of a solid or liquid, not gas. Gases can be adsorbate, but gases cannot be adsorbent. Let me tell you what is the difference between adsorbate and adsorbent. What is adsorbate and what is adsorbent? Just like in a solution, solute and solvent is there. Solute is the one which is dissolved in solvent, and solvent is the one in which solute is dissolved. Simple. In this case also, adsorbate is the one which is adsorbed and adsorbent is the one which adsorbs. Understood? If the solid or liquid is adsorbing a particular molecular species, then those molecular species will be known as adsorbate and the particular solid or liquid will be known as adsorbent. I think it is clear to you, I think. Okay, now we know what is adsorption. Now we know what is the difference between adsorption and absorption. Let us come to what are the types of adsorption. Actually, two types of adsorptions are there. Okay, two types of adsorptions are there. Number one, physical adsorption, and number 2, chemical adsorption. Physical adsorption, chemical adsorption. Physical adsorption is also known as physisorption, and chemical adsorption is also known as chemisorption. Okay, physical adsorption is known as physisorption, chemical adsorption is known as chemisorption. What is the basic difference between physisorption and chemisorption? Easy. Physical means only physical change will be there, and chemisorption, chemical adsorption must be chemical reaction. Okay, if a chemical reaction is taking place, between adsorbate and adsorbent, then the phenomena will be known as chemisorption. If no chemical reaction is taking place between adsorbate and adsorbent, then the phenomena will be known as physisorption. Let us discuss some of the properties of physisorptions and chemisorption. Some of the properties of physisorption and chemisorption. So let us start with physisorption. Okay, when we are learning about the properties of physisorption and chemisorption, simultaneously I will tell you what are the difference between physisorption and chemisorption. Is that okay? Okay, physisorption's property. Property number 1, lack of specificity. Property number 2, nature of adsorbate. Number 3, reversible nature. Number 4, surface area of adsorbent. Surface area of adsorbent. And number 5, enthalpy of adsorption. Enthalpy of adsorption. Okay, these are the properties, okay, of physisorption. Number 1, let me discuss what is lack of specificity. In physisorption, the adsorbent, the relation between an adsorbent and adsorbate is not specific. Let me give you an example. Suppose a piece of charcoal is there to create vacuum. So that piece of charcoal will absorb okay, whenever I am saying adsorb, you will have to consider it as adsorption, because we are in the chapter where we are learning adsorption. So maybe because of the pronunciation, some of you may think get confused that sir has told adsorption or as absorption. Which one is correct? I am telling you all the time it is adsorption. Okay, now if a piece of charcoal is there to create vacuum, it will absorb all the gases present in that jar. Okay, it will not show any particular attraction towards hydrogen gas or nitrogen gas or oxygen gas. Okay, so simple, it will attract all the gases with equal efficiency. Is that clear? So this proves that physisorption is actually non-specific. Okay, number 2 point, nature of adsorbate. Obviously nature of adsorbate is very much important. If the gas, suppose a gas is adsorbed, in a case where gas is adsorbed, then the gases which are easy to be liquefied, the gases which are easily liquefiable, the gases which are easily liquefiable can be adsorbed with a greater rate. Okay, and if a gas is not as easy to liquefy, then the rate of adsorption will also be less. So let me give you some example which are very difficult to be liquefied. For example, the gases like H2, O2, N2, these are not non-liquefiable. Actually, they are liquefiable but not easy. And the gases like NH3, SO2, these gases are easily liquefiable, and that is why these gases are easily adsorbed. Is that clear? Number 3, reversible nature. We are talking about physisorption. So all the processes are physical changes. That is why physical changes are reversible in nature. So this is reversible. Okay, if a charcoal can adsorb certain amount of gases, then by giving heat, that charcoal can give out the gases adsorbed, okay, to the nature also. So this process is reversible. No need to worry. Surface area of the adsorbent. To do that, I need to show you a diagram. Please see carefully. Suppose there is an adsorbent which looks like this. Okay, charcoal. Now I have taken two pieces of this kind of charcoal. One piece I kept it as a whole, and the other piece I converted it into powdered form. Okay, powder form. Now the question is, which one will adsorb easily? This one will adsorb easily. Why? Because the surface area of the powder is more than the solid one. Okay, the surface area of the powder is more than the solid one. Okay, so that is why this one is easier, and this one will adsorb with a faster rate, and this one will adsorb with a slower rate. Clear? So more the surface area, more will be the tendency to adsorb. Okay, last point, enthalpy of adsorption. In case of physisorption, the enthalpy is very less. In case of physisorption, the enthalpy of adsorption is very less. Why? Because the force of attraction, the kind of force of attraction which is acting in between the adsorbate and adsorbent, in case of physisorption, is van der Waals force of attraction, which is very weak. And because of that weak van der Waals force of attraction, delta H value varies between 20 to 40 kilojoule mole inverse. Is that clear? So the value of delta H is very less. That is why, value of delta H is very less in case of physisorption. Is that clear to everyone? Now let us discuss the properties of chemisorption. First point was lack of specificity in case of physisorption. Let us discuss the same aspect. Okay, in case of chemisorption, they are very much high. They are highly specific in nature. Chemical reaction is taking place now. So bonding can occur. Hydrogen can react only with oxygen to form water. Hydrogen cannot react with sulfur to form water. Simple. So hydrogen is specific about that. So in that way, in case of chemisorption also, they are highly specific. One particular adsorbent will adsorb one particular adsorbate, and that adsorbent will practically react with the adsorbate to form a substance and continue the chemisorption process. Okay. Number 2, irreversibility. Physisorptions are reversible, but chemisorptions are not reversible. Why? Because chemical reaction is taking place. Simple. Okay, let us come to the third point, which is what? Surface area. Surface area same. More the surface area, more will be the rate of adsorption. Next one, enthalpy of adsorption. In case of chemisorption, the enthalpy is very high. Enthalpy is very high. Why? Because chemical reaction is taking place. Now, so enthalpy of adsorption will be high, and the value of enthalpy of adsorption remains in between 80 to 240 kilojoule mole inverse. Okay, kilojoule mole inverse. So here are the properties of physisorption and chemisorption. Okay, and if you follow book, you will get the difference between physisorption and chemisorption. No need to discuss it here. Okay, so adsorption isotherm. Let us come to the next topic, which is adsorption isotherm. Adsorption isotherm. Adsorption isotherm. What is adsorption isotherm? Actually, there is a scientist whose name is Freundlich. Let me tell you, write you the spelling of that. Freundlich. Freundlich adsorption isotherm. This scientist gave a relation. Okay, gave a relation in between the pressure. The amount of gas. This scientist gave a relationship in between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by the following equation. I am writing the equation just now. Okay, the equation is x by m is equal to k into p to the power 1 by n. This is the equation. This is the equation. What is the significance of this equation? What does this ax, am, k, p means? Ax is equal to, x is actually is the the amount of gas adsorbed. The amount of gas adsorbed is x on mass m of adsorbent. K is a constant, p is pressure, and n is also a constant. Okay. And if you plot x by just hold on a second. If you plot x by m against pressure, what curve you will get? X by m pressure. What curve you will get? The curve that we will get is understood. The ratio of x and m will decrease with increasing temperature. Okay, with increasing temperature. This is the relationship between x by m and k and x by m and p. Okay, so let us carry on with this equation. Let us carry on with this equation. What was the equation? X by m equal to k into p to the power 1 by n. If we bring log to both the sides, what we will get? Log x by m equal to log k plus 1 by n log p. 1 by n log p. Okay, if you look at this equation, what do you see? I can see y is equal to mx plus c kind of equation. Y is equal to mx plus c, but m is the slope. Okay, and c is the constant, you know. Okay, so what will be the curve now? What will be the curve now if I put log x by m to the y axis and log p to the x axis? What you will get? This kind of curve I will get. A straight line, and this slope will be what? 1 by n. Is that clear? Okay, and this is the value of log k. Is that clear? So this is the actually Freundlich and Freundlich adsorption isotherm theory. Okay, and there is a practical input output of this theory. No need to discuss it now. Okay, and this theory is also true for the solution, not only for gases, for the solution as well. You know, for the gases, the one and only most important property is pressure, but in case of solution, the one and only most important property is concentration. So we can express the same equation, k into c to the power 1 by n, just changed p into c. Why? We are discussing about the solution. Okay, and we can continue the whole process. We can do the same whole process to get a relationship in case of a solution. Okay, so let us come to the next topic, applications of adsorption. There are many applications. For example, by applying adsorption theory, we can prepare gas mask, we can prepare high vacuum. Okay, we can control the humidity of weather, humidity of the air. We can remove coloring matter from solutions. We can separate inert gases. Okay, some diseases can also be cured by this process. Okay, so adsorption indicators can also be made by this process. Okay, and the chromatographic analysis is somehow dependent on adsorption theory. So these are the applications. If you go through the book, you will get more and more details. Okay, for that, go to the book, and if that is not enough, ask your teacher. Teachers are also always there to help you out. Now let us come to the next topic, which is colloids. Okay, you heard about colloids, you read about colloids in previous classes, and this time it will be in details. That is why it is important for you to pay attention to this class. Okay, what are colloids? Everyone knows the situation in between true solution and suspension is known as colloids. Okay, so colloids are of many types: solid in liquid, liquid in solid, solid in gas, gas in liquid. Many types of combinations are there, and examples are also there. For your reference, I can show you some examples. Just look at the camera very carefully. Okay, some examples. Solid in solid colloids example. Okay, no need to look at the camera. Actually, I'm telling you the examples. Solid in solid examples. The type of colloid that is found is solid sol, and examples are some colored glasses and gemstones. Solid in liquid, paints, cell fluids, etc. Liquid in gas, aerosol, fog, mist, cloud, etc. So in that way, many examples are there in our syllabus, in our book. Please go through that. But the main and the most important thing that needs to be understood is what is dispersed phase and dispersion medium. What is dispersed phase and dispersion medium? Same as solute and solvent. Solute is the one which is dissolved in solvent, and solvent is the one in which solute is dissolved. Dispersed phase is the one which is dissolved in dispersion medium. In place of dissolved, what will you say? Dispersed over dispersion medium. Dispersed phase is the phase which is dispersed over dispersion medium, and dispersion medium is the one in which dispersed phase is dispersed. Okay, so simple thing, dispersed phase. Suppose a gas is dissolved in liquid, so that gas will be called as dispersed phase, and the liquid will be called as dispersion medium. Okay, a colloid is there. For example, in case of smoke, actually it is an aerosol, and here solid is dispersed over gas. So in case of smoke, what will you say? Solid carbon particles are dispersed over air and forms what? Smoke. Simple. So that is dispersed phase and dispersion medium. Colloids can also be classified into two. Classified into two on the basis of the attraction between the interaction between the dispersed phase and dispersion medium. One is known as lyophilic colloids, and the other one is known as lyophobic colloids. Lyophilic colloids and lyophobic colloids. Lyophilic means what? If there is an attraction force, if there is a deep attraction between the dispersed phase and dispersion medium, then the colloids so formed will be called as lyophilic colloids. There is a chance of coagulation because of this attraction force. And lyophobic, what? Lyophobic colloids, lyophobic is the opposite of lyophilic. If there is no attraction force between the dispersed phase and dispersion medium, or the attraction force is very much less, then we will call it lyophobic colloids, and peptidization is a result of lyophobic colloid. Okay, so we will get deep into that topic, no need to worry. And colloids can also be classified into three categories on the basis of what? On the basis of type of particle of the dispersed phase. Okay, number one, multimolecular colloids. Multimolecular colloids in which a large number of atoms or smaller molecules of a substance aggregate together to form a species having size in the colloidal range 1 to 1000 nanometer. And macromolecular colloids, number two, macromolecules in the suitable solvents form solutions in which the size of the macromolecules may be in the colloidal range. Okay, true solution in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins. These are examples of macromolecular colloids. Associated colloids, number three, which is also known as micelles. It is a very important term, associated colloids or micelles. Now I am going to tell you how micelle is formed. Okay, and taking an example of soap solution. I am going to tell what is micelle formation. It is very much simple. No need to just get confused or nervous. Okay, what is the formula of soap? Can anyone tell me? Actually, this is video recording. I cannot say anyone tell me. Okay, sodium stearate is the formula of soap. Sodium or potassium stearate is the formula of soap. And what is the name of soap? Okay, and what is the formula? It is C17H35 COONA, positive, negative. This is the formula of what? This is the formula of soap, C17H35 COO negative, Na positive. And how does it look like? It looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 CO minus. Okay, and you already know what these corners and ends mean. It means hydrocarbons like C and H. Okay, so this is the whole structure of what? Sodium stearate. Only stearate ion. Sodium is there, Na positive. Okay, so now see this. Whenever we dissolve soap into water, this dissociates into COO minus and Na positive ions. Okay, Na positive ions. Now the main thing that functions as a soap is this stearate ion. Now the point is what? The point is this part of this stearate ion is highly lyophilic and the rest part is lyophobic. Lyophobic means which has no attraction towards the solvent or the dispersion medium. If the dispersion medium is water, then we can call it as hydrophobic. We can call it as hydrophilic. So hydrophobic, hydrophilic. So this hydrophobic part and the hydrophilic part both are present where in the stearatine. So stearatine can also be shown in that way. Okay, I'm showing this circle to denote what, to just to show the lyophilic part, and this tail, the hydrocarbon tail, is to denote the lyophobic part. Okay, now both of them has a function, a role to play. Now let us discuss. Okay, what is it? Now whenever you take some water into beaker and pour soap solution, what actually happens? Okay, this happens. Okay, whenever comes inside the water molecules, the lyophilic part will be highly attracted towards these water molecules, but the lyophobic part will not feel safe. So there is a problem. Stearate ion is an ion in which lyophobic and lyophilic both parts are present, and the lyophilic part is feeling safe while dissolved in water, but the lyophobic part is not feeling safe while dissolved in water. So what happens next? Why do we use a soap? Can anyone tell me? We use soap for because it has a cleansing action, it has a cleansing property. So whenever the cleansing quality is there in soap solution, I can show you the procedure. Okay, what exactly happened? Suppose some dust particles, suppose some oily marks are there in your shirt, and those oily marks, suppose this is a droplet of an oil, suppose, then what happens? The lyophilic head stays outside. Okay, so all the lyophilic parts are there outside this oily mark, and the lyophobic part inside the oil. Why? Now this lyophobic as hydrophobic, these hydrocarbon tails are hydrophobic, and this area is actually oil, and this area, the rest area of the board, is actually water. Okay, so the lyophilic part, the hydrophilic part stays inside the water, and the hydrophobic part stays inside the oil, away from the water. So this particular thing is called micelle. Okay, this particular thing is called micelle, and this process is known as micelle formation. And by micelle formation, and this is also known as associated colloid. Okay, so this by this micelle formation, soap solution shows its cleansing property. Now let us come to the next point, which is how colloids are prepared. Colloids can be prepared into two ways: in the laboratory by chemical methods, and in the industry by using electrical method. Okay, now chemical methods are as follows. Just I'm writing the equations, just follow. Arsenic oxide is 2O3 plus hydrogen sulfide H2S gives what? Double decomposition As2S3 plus As2S3 plus what? 3H2O. Simple. So this As2S3 is a colloid, Okay, this is the colloidal part, and this is the chemical process by which arsenic sulfide is prepared. Some more examples. Let me give you another example. Gold sol. How can gold sol be prepared? Okay, just I'm erasing it. I'm going to write the equation. 2AuCl3. Write it down, everyone. 2AuCl3 plus 3HCHO plus 3H2O gives 2Au plus 3HCOOH plus 6HCl. This one is the sol. Sol means colloid, nothing else. So this is how gold sol is prepared. Now let it go. Let us come to what? Let us come to the next one, which is electrical method, and this method is also known as Bradig's arc method. Bradig's arc method, what happens actually in Bradig's arc method? I am dictating, listen very carefully. This process involves dispersion as well as condensation. Colloidal salts of metals such as gold, silver, platinum, etc. can be prepared by this method. In this method, electric arc is struck between electrodes of the metal immersed in the dispersion medium. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. Simple. First, it is vaporized, then it is condensed, and when it is condensed, then what happens? It stays in between solid and gas and makes a colloidal sol of the metal. Gold, silver, platinum, the only noble metals salts can be prepared by this method. Okay, now there is another thing by which colloids can be prepared. It is peptization. What is peptization? It is a very important one. This comes in the examination. Peptization. What is peptization? Peptization is the process by which colloids can be prepared. Okay, peptization may be defined as a process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. This method is applied generally to convert a freshly prepared precipitate into a colloidal sol. Sometimes it happens colloidal particles actually forms a large size of, actually coagulates to form a larger size of molecules, and those molecules does not range in between colloidal size, and that is why it is converted into suspension, and the sediments is collected at the bottom of the solution, and those sediments are known as precipitate, and the whole process is known as coagulation. Now those coagulated particles can also be converted into colloids again, and the process by which those coagulated particles are being converted into colloid is called peptization. So coagulation and peptization both are related to each other. In coagulation, what happens? Precipitate is formed, and in peptization, what happens? Those precipitates are again converted into colloidal solution. Okay, so this is a simple fact. Don't just confuse with both these terms. Both these terms are opposite to each other. Coagulation needs a coagulating agent, and peptization needs a peptizing agent. Peptizing agent is always an electrolyte which divides the greater molecules into smaller parts, and coagulation agents are those which helps in combining the smaller molecule to form larger sized molecules. Simple. Now let us come to what is Brownian motion, to the next topic, which is Brownian motion. What is Brownian motion? You must have read about this in class 9. What is Brownian motion? Brownian motion is the zigzag motion of the dispersed phase over dispersion medium in a colloidal solution. Okay, so zigzag motion. So dispersed particles are moving like in that way. Okay, so this is called Brownian motion, nothing more. Okay, so the Brownian motion is an important topic, but Brownian motion is seen only in colloids. Okay, now what is Brownian motion? I told you. Now what is the point? What are charged charge on colloidal particles? What are the charges that can be present in colloidal particles? Colloidal particles may be positive or may be negative or may be neutral. So three types of colloids are there on the basis of charge: positive, negative and neutral. So the neutral one is also made up of two parts, one positive part and one negative part, just like sodium stearate. Okay, so charge on colloidal particles, let me give you some examples of positively charged salts and negatively charged salts. Some positively charged salts are aluminum oxide, chromium oxide and iron oxide. These are positively charged salt, and some negative salts are copper, silver, gold. So metallic salts are negatively charged salts, and some hydrated oxides, hydrated aluminum oxide, hydrated chromium oxide, hydrated iron oxide. These are examples of positively charged colloids. Some examples of positively charged salts are also hemoglobin and and negatively charged acid dyestuffs. Okay, eosine, congorate salts. These are also negatively charged salts. So these are positively charged salts and negatively charged salts. Let me just go deeper into this matter. Okay, when highly diluted solution of silver nitrate is added to highly diluted potassium iodide solution, the precipitate silver iodide absorbs iodide ions from the dispersion medium and negatively charged colloidal salt results. However, when Ki solution is added to AgNO3 solution, positively charged salt results due to absorption of Ag plus ions in the dispersion medium. It's very simple. Okay, highly diluted what did I take? Highly diluted silver nitrate. Highly diluted silver nitrate is taken and highly diluted potassium iodide is taken. Whenever they are reacted with each other, AgI is formed and KNO3 is formed. KNO3 is soluble, just leave it. This one is the main thing. This AgI does what? This AgI, actually I didn't take one molecule of Ki. There are several molecules of Ki, and Ki dissociates as like this: Ki, K plus I minus. So these I minus are again attracted by AgIs to form what? Sol of AgI and I. Okay, they coagulate, actually they combine with each other to form a larger molecule which ranges in between 1 to 1000 nanometer. Okay, so this is the process. It is the process by which negatively charged colloids can be prepared. If more amount of Ki is dissolved, what happens? More amount of Ki is dissolved, or more amount of Ki is dissolved, then AgI will attract Ag plus. Okay, sorry, just hold on a second. When Ki solution is added to AgNO3 solution, okay, more Ki is added, then AgNO3 will also be dissociated into like that now, Ag plus NO3 minus, and this Ag plus ions will also be attracted to this to form what? AgI oblique Ag plus. So this is an example of positively charged salt. So in that way, positively charged salts and negatively charged salts are prepared. Okay. Now what is electrophoresis? Write it down, everyone. The colloidal particles move towards oppositely charged electrodes. They gets discharged and precipitated, and this process is known as what? Electrophoresis. Electrophoresis is a process. Electrophoresis, no need to discuss it. Okay, its details is given in the book. Okay, go through that. What is emulsion? Anyone knows? A liquid colloidal system is called emulsion. An example, milk. In milk is an emulsion. Oil dispersed in water and water dispersed in oil. Two types of emulsions are there. Okay, when oil is dispersed over water, that is a type, and when water is dispersed over oil, that is another type. Okay, emulsion of oil in water are unstable, but emulsion of water in oil is very much stable. Okay, some examples of oil in water emulsion is long chain alcohols, lamp blacks, heavy metal salts, fatty acids, etc. are some water in oil emulsions example is what? Milk, etc. Okay. Colloids around us. Many examples are there. Blue color of the sky. Fog. Why the sky appears to be blue? The answer is what? Dust particles along with water suspended in air scatter blue light which reaches our eye and the sky looks blue to us. Simple. Fog, food articles, blood, all these things are made up of colloids. Okay. This is where our chapter ends. Thank you everyone. And if you find any difficulties, you let me know, or let your teachers know, respective teachers. Okay, they will actually help you out.